Welcome to the flight deck. Today's explainer is all about the Bombardier Q400, specifically how to handle a very specific high workload scenario. Picture this. You're coming in hot on approach and bam, you get an abnormal flap failure. Your flaps are stuck somewhere between 0 and 10 degrees. So how do we get this high-performance turboprop safely onto the tarmac? Let's walk through the exact chronological sequence so you're totally ready for it. Here's our exact cockpit flow for this explainer. We'll start with the initial setup in autopilot, move into pitch, power, and touchdown, cover brake energy and performance, calculate our approach and landing speeds, and wrap up with some crucial final cautions.
Okay, moving right into part 1, initial setup in autopilot, reacting to the failure.
The second you identify that flap failure between 0 and 10, your reaction needs to be immediate, right? To lock this in, we're going to use a handy acronym, GAP, literally GAP. The G stands for GPWS. Your very first move is to press that GPWS flap override. You want to silence the ground proximity warning system right away so it doesn't distract you with a bunch of false alarms about your flap configuration. Then comes the A for autopilot. Step 2 is to disengage the autopilot at 1,000 feet above ground level. But, and this is a big but, you only do this if your flap setting is less than 5 degrees. Boom, you're now hand-flying the machine.
Let's transition to part 2, pitch, power, and touchdown, managing the flare.
So as we get closer to the ground, we hit the P in our GAP trick, pitch and power management. Because you've got a reduced flap setting, the aerodynamics of the Q400 are just fundamentally different here. You're coming in faster, so energy management is absolutely crucial. Now, depending on your environment, you're likely looking at one of two scenarios. In scenario A, your landing descent rate is higher than you want. You actually have to use power in the landing flare all the way through to touchdown. Why? Simply to decrease that descent rate so you don't pitch up past 6 degrees. Scenario B is a similar aerodynamic puzzle. If you're landing at a high-altitude airport, anything over 5,000 feet, that thinner air means you're also going to need to maintain power right through the flare to soften the descent. Two totally different challenges, but they share the exact same power solution.
All right, on to part 3, brake energy and performance. What happens on the ground?
Now the wheels are actually on the tarmac, but hey, the emergency isn't over yet. With flaps between 0 and 10, this aircraft carries a ton more kinetic energy than normal. Immediately after the main wheels touch down, you need to promptly bring the nose wheel into contact with the runway. Just get the aircraft firmly planted. And you really need to heed this warning. Those high landing speeds mean you could literally exceed your brake kinetic energy limits. To manage this without overcomplicating the math in a stressful moment, I want you to remember this rule. Smaller is safer. If your flaps failed somewhere between the gated positions, you always use the smaller flap angle for your performance calculations.
Which leads us perfectly into part 4, approach and landing speeds, the actual calculation.
So let's apply that smaller is safer rule to the actual data. We know we're coming in fast, but how fast? Let's look at our VREF speeds. If you're stuck between 0 and 5, you use flap 0. Stuck between 5 and 10, you use flap 5. Simple enough, right? For flap 0, with the reference speed increment on, your base is 1.23 VSR, that's your reference stall speed, and your target is that base plus 25 knots. If you're using flap 5, your base is exactly the same, 1.23 VSR, but your increment is just a bit lower at plus 20 knots. This data is literally your lifeline for setting up a stable approach.
Now, what's really interesting about these landing distance factors is the symmetry. Whether you're doing the math for flap 0 or flap 5, the procedure dictates that you use the flap 35 chart as your baseline. From there, both settings share the exact same landing distance multipliers. You're just going to apply a factor of either 2.0 or 2.5 depending on your specific operational requirements. It's incredibly easy to remember in a high workload situation. Flap 35 chart times 2.0 or 2.5. Done.
Finally, we arrive at part 5, crucial final cautions, the rule of 6s and 150s.
We've set up the approach and calculated our speeds, but before we wrap up, I want to introduce one last memory trick, the rule of 6s and 150s. This anchors the absolute most critical safety warnings of this entire procedure. First up, the 6. Caution: avoid pitch attitudes in excess of 6 degrees at touchdown. I really want to emphasize that. Do not exceed 6 degrees. Because you're carrying extra speed and holding power through the flare, pulling the nose up too high is practically guaranteeing a tail strike. 6 degrees is your absolute hard limit.
And here is the second half of that rule, 150 knots. Do not select your power levers below flight idle until your indicated airspeed drops below 150 knots. If you pull the power back too far while you still have all that forward momentum, you're creating a massive, highly unsafe aerodynamic drag profile on those huge propellers. Just be patient, let the speed bleed off, and once you're under 150 knots, you're clear to bring them back.
So, let's bring it all together. Think about the GAP trick, the smaller is safer rule, and our rule of 6s and 150s. How much will mastering this exact chronological flow change your reaction time the next time those warning lights flash in the Q400? Having that structure creates calmness, and in the cockpit, calmness creates safety. Thanks for joining me for this explainer, and I'll catch you on the next one.